Alright, so we're going to talk about conditional statements. So a conditional statement is a statement that has two parts in the form of an if-then. And those are going to be critical words when we look through these statements. So if and then are really breakpoints for things that we call the hypothesis and then the conclusion. So the hypothesis follows the if, the conclusion follows the then. If we symbolically want to put this in shorthand, we would often write it something like this: P arrow Q, which stands for if P, then Q. So something like if it's Saturday, then it's a weekend. Something that we set up a hypothesis or something that happens, and then we have a conclusion that follows directly from that hypothesis. So a conditional can have a truth value of either true or false. So we could say statements that are false, but often we're going to be more interested in things that are true. We're going to try to prove things that have a truth value of being true. So here below is a conditional statement. If x squared is greater than or equal to 0, then x is greater than or equal to 0. So the hypothesis is x squared is greater than or equal to 0. It comes after the if. The conclusion is x is greater than or equal to 0, which comes after the then. In terms of the truth value, it's false. I could take a negative value, like -4, and then square it and get a value greater than 0. However, x itself wasn't greater than 0, which was my conclusion, the thing after the then value. Okay, so we can also use Venn diagrams to show what these look like. So Venn diagram, you use them in different classes, maybe your science class. But if we look at this statement, all cats are animals. Well, we can see within our diagram here, all cats are contained with, mammals, within of our mammals diagram. So it's a subset of the mammals population. The converse of a condition switches the hypothesis and the conclusion. And so for our example above, we take the mammals and switch it with our hypothesis, so all mammals are cats. And this is often hard to wrap your head around, but the converse might not be true if we flip a statement around. So let's look at these examples on here. We'll look at the converse and then go from there. So my hypothesis is x equals 9. My conclusion and x squared equals 25. Those are my two hypotheses. The conclusion, what comes after then, are x plus 3 equals 12 and x equals 5. If I want to write the converse, then I switch those pieces around. So if x plus 3 equals 12, then x equals 9. And if x equals 5, then x squared equals 25. So you can see what we're doing is we're taking the conclusion and it becomes a hypothesis, and the hypothesis becomes a conclusion. So if we look at the truth value, the first one is true. The second one is true. So we don't have our we don't have counterexamples for these. If we look at our value here, if x squared equals 25, then x equals 5. So our original statement, well, that could be false, as x equals -5, which are a counterexample to our original statement up here. Okay. Once we start turning things around and looking at truth values, we come across something called a biconditional. So when a conditional and its converse are both true, we combine them as a biconditional. So bi meaning two, it really can be written as two conditional statements. What we usually do to connect them is if and only if. So if and only if both things happen does this work. Symbolically, P then Q, Q then P, and then we bring it with the double arrow, which means P if and only if Q happens. Okay, so let's look at this example. Consider the conditional, the true conditional statement below. Write its converse. If the converse is also true, combine the statements as a biconditional. Here's our conditional. If you live in California, then you live in the most populated state, in the U.S. So the converse, we switch it around. If you live in the most populated state in the U.S., then you live in California. And as a biconditional, because that's true, you live in California if and only if you live in the most populated state in the United States. So that's how we combine them. We no longer have an if and then, but we can see that we've taken this if and only if, and it replaces it if and only if you live here does this work. Because this, remember this arrow, the one at the top here, it goes back and forth between the two. So here's another one. We'll look at the converse and the biconditional. So that is my conclusion, right? So I want to start with that. If x plus 15 equals 20, then x equals 5. That's true. And so we have a biconditional. We can write x equals 5 if and only if x plus 15 equals 20. So we also have, in geometry, it becomes really important that we have good definitions because we want to be very specific about the pieces that we're looking at. So if we look at these statements, good definitions are statements that can help you identify or classify an object. They need to be precise. They need to use commonly understood words. It doesn't help if we have a lot of jargon in there. Is reversible, right? Which means that we really want to be able to write it as a biconditional. It should be able to go back and forth. And so here's an example of a good definition. A triangle is a polygon with exactly 3 sides. It's reversible. So we could write the conditional. If a triangle is if a polygon is a triangle, then it has 3 sides. And that's true. If we have the converse, if a polygon has 3 sides, then it's a triangle. And so now we can combine it into a biconditional. A polygon is a triangle if and only if it has 3 sides. Right? And so that takes all of those and shows that it goes both ways, 3 sides or being a triangle, and that those can lead to both statements being true.